All right, so a projectile of mass 2 kgs is fired in the air at an angle of 40 degrees to the horizon at a speed of 50 meters per second. Again, 50, about 10 meters per second is about 20 miles an hour, 25 miles an hour. So that's 130 miles, 125 miles an hour. Okay, so quite fast. At the highest point in its flight, the projectile breaks into three parts. Okay, so when you shoot a projectile, it goes on a parabolic trajectory, and at the highest point, the y component of its velocity is 0. Okay. Again, the velocity is always tangent to the path, and at the highest point, the velocity is horizontal, so it has only an x component. Okay, so its momentum is in the x direction. And then what happens? At the highest point, it breaks up into three parts. At the highest point in its flight, the projectile breaks into three parts of mass 1 kg, 0.7 kg, and 0.3 kgs. They add up to 2 kgs. The 1 kg part falls straight down. So they break up into three parts. One part falls straight down. With an initial speed of 10 meters per second and mass of 1 kg. The 0.7 kg part moves in the original forward direction. So here's one piece, 0.7 kgs. And the 0.3 kg part goes straight up. So okay. And they say find the speed of the 0.3 kg and 0.7 kg pieces. So we want to find the speed of this guy and this guy. This guy is going at 10 meters per second. How high from the breakup point does the 0.3 kg piece go? So the faster it's going, the higher it'll go. Okay, and then it'll fall straight down. Where does the 0.7 kg piece land relative to where it was fired? So, and then this will go on a parabolic trajectory, and the question is, where will it fall? Okay. So this problem has several parts to it, but it'll illustrate many of the principles that you've seen. And this one problem contains several, 2-3 problems. All right, so at the top of the trajectory, what this piece has is, it has momentum in the x direction. The momentum in the y direction is 0. And now when this explodes, it could explode into 1,000,000 pieces. After the explosion, the sum of all the 1,000,000 pieces should be equal to what the momentum was just before the collision. Just before the explosion. Okay? So for instance, in this case, it broke up into three pieces. The momentum of these three pieces should be in the x direction. So that means this momentum should cancel that momentum. Right? This is a momentum in the positive y direction. This is a momentum in the negative y direction. So those momentum should add up to 0. Okay? And the momentum of this guy should equal the momentum of the original piece in the x direction. Did you guys understand that? So this guy was 2 kgs, and he was going at, let's say, I don't know the speed, but let's say he's going at 3 meters per second. So the momentum in this direction would be 6, 2 times 3, 6. And so this guy should have 0.7 times whatever speed equals 6. Okay? That's how we'll solve that. Did you guys understand all of that? All right, so now what we'll do is, so here was the initial speed, V naught. The initial speed is 50 meters per second, and he was fired at 40 meters per second. So V naught x is equal to 50 meters times cosine 40. And okay, so that is the initial component of the x velocity. So that'll be the velocity of this 2 kg piece at the top of the trajectory. Okay, and so I'm going to, you have to understand all of this. So find the speed of 3 kg and 7 kg pieces. So let's find the speed of the 7 kg piece. Okay, so 2 kgs into 38.3 meters per second should equal 0.7 kgs times v 0.7. Did you guys understand that? So this had only x component of the momentum, and that'll be equal to that. Okay. So v 0.7 equal to 2 times 38.3 divided by 0.7. Okay, so you see, the smaller the mass, greater the speed. The mass is smaller by a factor of 2.5 roughly, and the speed is greater by a factor of 2.5 roughly. Okay. All right, now we'll find the speed of this guy. So the y momentum should be 0. So, and if you guys want, we'll write py equal to 0 is equal to 0.3 times v 0.3 minus this momentum is negative, minus 1 times 10 meters per second. Okay. So v 0.3 is 10 divided by 0.3, which is 33.3. Okay. So what we have done is we found the speed of this guy, which is 110 meters per second, and we found the speed of this guy, which is 33.3 meters per second. Okay. And now we can solve these parts. See, the faster this guy is going, the higher he'll rise. Okay, so that's that part. How high from the breakup point does the 0.3 kg go before coming to rest? And then where does the 0.7 kg piece land relative to where it was fired? So we'll find how far he travels, and then we'll calculate that total distance. Yep. All right, so part B. Now part B is you're shooting this guy at 33 meters per second, and his acceleration is in this direction. So we'll call this y naught, y minus y naught equal to v naught y. Now what we'll do is we'll v square equal to v naught square. Okay. So this is what we want to find. How high does he rise? Okay. Okay, so he was shot at 33 meters per second. What is his speed at the top? 0. So this will be 0. Okay. And the acceleration is negative 9.8 meters per second squared. Okay. And so this works out to so y minus y naught okay. So this is 33.3 meters per second is roughly 75 miles an hour. So if you throw a baseball at 75 miles an hour, it'll rise up 56 meters. Okay. 56 meters is roughly the tallest building on the beach. Okay. All right, now part C, where does the 0.7 kg piece land relative to where it was fired from? Okay, so this is a parabolic trajectory. This was V naught was, what was it, 50 meters per second? Yep, 50 meters per second. This goes on a parabolic trajectory, and at the top, and then at the top it acquires, because of the explosion, it's going at 109.4 meters per second. So since he's going faster, he'll go on a wider parabolic trajectory. Okay. And we will find what we'll do is we'll find this distance, and okay, so that'll be two separate problems. Okay. And your total distance will be d1 plus d2. Yep. All right. Now, had he not exploded, that would be the range formula. Okay. Actually, I won't use the range formula. I'll just calculate the time of flight, and then we'll calculate this distance. Okay. So we'll do d1. Okay. So what has happened to the y component of the velocity at the top? It's become 0. So Vy equal to V naught y plus Ay times t. Vy is 0. V naught y is 50 times sine 40 minus 9.8 t. Okay, so that's how long it took to go from here to there. And so let's calculate how far will it travel along the x direction. Okay. So d1 equal to x minus x naught equal to v naught x t plus 1/2 ax t square. The acceleration in the x direction is 0. So d1 equal to 50 cosine 40 times 3.28 seconds. 125.6 meters. All right. Now, notice the following. See, the y component of the motion is independent of the x component. So, I don't know if you guys can see this. See, the y component, initial y component of the velocity was this. And if had it gone with this velocity, had it gone straight up, it would have taken the same amount of time, 3.28 seconds. This guy will take the same amount of time to fall that distance. Okay? All right, so now we can calculate, if you understand that, so to rise and fall, it takes the same amount of time. Okay? So now calculating d2 is easy. d2 is, again, x minus x naught v naught xt plus 1/2 ax t squared. That's 0. Okay, now this guy's velocity is 109.4 meters. And before he hits the ground, his time of flight is that many seconds. Okay, so the total distance is travel. So this total distance, okay, so that little piece falls this far away from the launch point, and which is okay, so 84.4 meters. Okay. All right. All right, let me summarize that problem again. I'll pause a second. If you guys have any questions on that? Okay, I urge you guys to study that problem carefully. Okay. It has a lot of parts to it, but it'll all illustrate all the things that you've learned. Okay, so you launch a 2 kg object at the top of its trajectory. You launch a 2 kg object at the top of its trajectory. When it has only x component of the momentum, it explodes into 3 pieces. And so the sum of the momenta of all these 3 pieces should equal this initial momentum. Since this initial momentum is only in the x direction, this momentum and this momentum should add up to 0. That's how we found there's this guy's speed. And the momentum of this guy should equal the momentum of this guy just before explosion. Okay. All right. Here's a similar problem, so I guess I'll do that. A 370 kg deer are standing on a flat 200 kg rock that is on an ice-covered pond. a gunshot goes off and the deer scatter with deer A running at 50 at that velocity, deer B running at, so all these velocities are two-dimensional velocities. They're not jumping, they're all horizontal velocities. Okay. And what is the velocity of the rock when they're standing? Okay, so there's the rock and there are the three deers, and the total initial momentum is 0. Okay, so let's say the rock goes this way, one deer goes that way, one deer goes this way. The final momentum has to add up to 0. Okay. And since these are two-dimensional vectors, so initial momentum equal to deer A plus deer B plus deer C plus rock should add up to 0. 0 vector. Okay. So that means mass of A times velocity of A plus mass of rock, velocity of rock should add up to 0. Okay. So the masses, so all their masses are 70 kg and the rock's mass is 200 kgs. Okay. So mass of deer VAX plus VBX plus VCX plus mass of rock VRX should equal 0. So 70 kgs times 15 minus 12. So this is the X component plus 1.2 should equal 200 plus 200 times VRX should equal 0. So the X component of the rock's velocity is okay, that's 3 plus 1.4.2 divided by 2. Okay, so negative 1.47, so we'll round it. Okay, 1. Okay. And the Y component similarly is okay. So the same equation except with the Y components. Okay, so I'll write that. Mass of deer times VAY plus VBY plus VCY plus mass of rock times VRY should add up to 0. 70 times 5 plus 8 minus 18 plus 200 times VRY equal to 0. And this is minus 5, so VRY is minus 350 divided by 200. Oh, that's minus 5, so that's plus 350. Okay, so 1.75 meters per second. So the velocity of the rock is negative 1.47 I plus 1.75 J meters per second. So the rock goes off in that direction. Okay. Any questions on that? Okay. So this problem says this is a center of mass problem. A cube of side A is cut out from another cube of side B. So A is smaller than B, as shown in the figure. Find the location of the center of mass of the structure. So they want you to find the center of mass of this fellow. Okay. Okay. Now, let's say you had the whole piece. So before you cut out, where was the center of mass? I'm sorry? At the center for the whole piece. For the whole piece. The center of mass would have been B by 2, B by 2, B by 2. Okay? So we'll call this M1. So let's say that's the mass of the whole piece. Let's imagine that this piece is there, its mass is M1, and the mass of this piece is M2. Okay? So if the whole piece, if both the pieces existed, the center of mass of this plus the center of mass of this, if both of these guys existed, the center of mass of the whole piece is that. So, okay, so we would use this formula. X center of mass is the mass of each piece times the x coordinate of the center of mass of that piece divided by the total mass. Okay. So what we are saying is if both the pieces existed, this B by 2 would equal M1. And what is the x coordinate of the center of mass of this piece? It's A by 2 plus M2 times x center of mass of the second piece, okay, and divided by the total mass. And this is what we're trying to find. The x coordinate of the center of mass of this piece. Okay. All right, now, so to solve for this, we want M1 and M2 in terms of M. Okay. So M1 is, the density of this thing is uniform, so it's A cubed, the fractional volume, times that. You guys understand? Okay. What is M2? What would M2 be? What is the volume of this guy? We want the fractional volume. What is the volume of that guy? B cubed minus A cubed. Okay. All right, so now we can plug those two in here and solve for that. So b by 2 equal to m1 is a cubed by b cubed times m times a by 2. That's that term. And then let me write this term, and I'll call it just x, plus b cubed minus a cubed divided by b cubed times m times x. X is what we're solving for, divided by m. Okay. So b by 2 equal to a cubed by b cubed times a by 2 plus b cubed minus a cubed times x. Pretty ugly looking expression. Okay. But so one of the things you got to make sure is this has to be positive. Okay, because its center of mass is somewhere there, it's got to be positive. Okay. And another thing is it's got to be greater than b by 2. Because for the whole piece, if the center of mass is over here, for this guy, the center of mass is somewhere over there. Okay, so it has to be greater than b by 2. Okay. All right. It is positive because a by 2 is less than this, and this fraction is less than 1. So b by 2 minus a smaller number, this is positive, and this is also positive, so this is positive. That's one verification. Okay. Now let's see if we can simplify this. Looks pretty ugly to me. It's I don't see any obvious simplification. Okay, let's see. All right, not bad. B cubed. This b cubed cancels. So this is equal to the x coordinate of the center is 1/2 b4 minus a4 divided by b cubed minus a cubed. Okay, that's not a bad expression. So what is this? This is the x coordinate of the center of mass of the second piece. The second piece being this guy. What is the y coordinate? Can you quickly tell me?
It's the same.
It's the same, very good. Okay, so from the symmetry of the problem, you see x, y, and z coordinate were the same, and the z coordinate would be the same. Okay, So for the second piece, so for M2, X, Y, and Z center of mass is equal to 1/2 B4 A4 divided by BQ minus AQ. And the same thing, okay? And so another thing we would want to show is that this is greater than B by 2. So 1/2 B to the power 4, A to the power 4, B cube minus A cube. You would want to show that. Okay. B4 minus A4, B cube minus A cube is greater than B. This is just an extra bit. B4 minus A4 is greater than B4 minus A cube B. Okay. So negative A4 is to the power 4 is greater than, so what you would want to show is A4 is less than A cube B, and this is true. B was greater than A, so this is greater than that. Okay. All right, let me quickly do a couple more problems. Okay, so again, what this problem was about was, okay, what we found was the center of mass of this piece. Okay, for a uniform density object, the center of mass is at the geometric center. So we found the center of mass of this guy, which was that. Okay. Okay, so here's another useful problem. It will help. Okay, so find the center of mass of a thin wire of mass m and length L bent in a semicircular shape. Okay, so you take a wire and bend it into a semicircle, and you want to find its center of mass. Okay, so if it was a full circle, then the center of mass would be right there. You know that. If it was a straight line, the center of mass would be at the center. Okay, now you bent it like so. Okay, from the symmetry of the problem, you know that it's on the y-axis. The center of mass is on the y-axis. Okay, so the center of mass is somewhere there. And that's what you want to find. Okay, so if you draw your axes like this, the x coordinate is 0, and the y for the center of mass, this is 0, y center of mass. Okay, and that's what you want to find. All right, so what we're going to do is, so this formula for the center of mass was for discrete masses. Okay, we have a similar expression when you have a continuous mass distribution, so we'll have to set up an integral. Okay, so we'll generalize this equation, and this is in your notes. Okay, so y center of mass, in the denominator you have the total mass of the wire, and then y dm. Okay, so that's the integral you have to do. Okay. And dm, so what we'll do is let's break this into little pieces. This is dm, okay, and we'll set up an integral over the angle theta. Okay, so 1 over m y dm. Okay, what is dm? dm is the mass of this little piece. dm is the mass of this little piece. Okay, And okay, so by the way, R is pi times R is L, so R is L over pi. dm is, okay, let's say that is d theta, that angle is d theta. Okay, so dm is r d theta. Okay, there's several things going on. R d theta is what? What is this guy? R d theta is the length of this arc. Okay, and the length of this arc divided by the total length times m gives you the mass of that little piece. Okay, so 1 over m y, and then y is this distance, that distance is y, which is r sine theta. dm is r d theta L times m. All right, so okay, so let's do this. So this is 1 over m the m cancels, and you have r square by L sine theta d theta. Okay, so effectively what you've done is you converted this integral into a theta integral. Okay, and what does theta change from? What are the limits of integration? What's that again? 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 0 to pi. Right. Okay. 0 to pi. All right, so there's y center of mass. Okay, r square by L, r square by L, and L was pi r, 0 to pi sine theta d theta. And negative cosine theta, 0 to pi. So minus cosine pi plus cosine 0. That's minus a minus 1 plus 1, 2 over pi r. And you see this is less than 1. So this is essentially 2/3 of r. So the center of mass is 2/3 of r. R is there, 2/3 of r. Okay. So again, so this is a good illustrative problem. It shows you how to set up integrals and stuff like that. Okay, so I'll review that. Okay, I'll do one more problem and then we'll I'll do this last problem and then we'll do the lecture in chapter 10. Okay, so this problem says how much fuel would be needed for a 1,000 kg rocket. This is its mass with no fuel to take off from Earth and reach 1,000 meters per second in 30 seconds. The exhaust speed is 1,000 meters per second. All right. So if you check your notes, um, okay, so what this formula tells you is this is the final speed of the rocket. That is the initial speed of the rocket. There's the exhaust velocity, natural log of initial mass of the rocket. That's on the launch pad, so that's the mass of the rocket plus the fuel. And this is the final mass of the rocket, so just the mass of the rocket. It's burnt all its fuel. This is the acceleration due to gravity, and that's how long it flew. Okay. So what we'll do is we'll calculate the initial mass. We know the final mass. So let me write it down, all these guys. 1,000 meters per second, the final velocity, 0. It starts off at 0. 1,000 meters per second is the exhaust velocity. Initial mass of the rocket, we don't know. Final mass of the rocket is 1,000 kgs, and I'm not writing down units, 9.8 meters per second square, and it flew for 30 seconds. All right, so 1,000 equal to 1,000. Okay, so mi over 1,000 is e to the power of 1.294. So the initial mass is okay, so the mass of fuel is this minus 1,000 kg. Okay, so mass of fuel is 2,647 kg. Okay, so again, this rocket is roughly 70% fuel. All right, guys, so we'll stop here.